Everyone, we are now ready for 5.1 exponential functions. An exponential function has the form where f of x equals a times b to the exponent of x. That's what makes it exponential, is the variable is in the exponent position, where a is the initial or starting amount, and the starting amount cannot be 0, and b is the growth or decay factor per unit of x, and b has to be greater than 0 and it cannot equal 1. So here's something to note about that growth or decay factor. If b is larger than 1, okay, then the exponential function increases, or we have growth. If that b value is between 0 and 1, then the exponential function decreases or decays. So think of b as the percentage of the original amount that you're getting back. Are you getting less back, or are you getting more than 100% back? So one thing to note is an exponential function grows or decays by a rate, okay, proportional to the amount present. So think of b as the percentage of your original amount that you're getting back. Are you getting more than 100%? Then you're getting more than your original, so it's growing. Are you getting only 85% of your original back? Then it's decreasing. So in our first example, we're modeling with exponential functions. It says the population growth of a small country is described by the function p of t equals 28 times a factor of 1.065 to the power of t. Note that our variable is in the exponent position. That tells us it is an exponential function. Now, t represents the number of years since 1990, and p, the population, is in millions. So they want us to determine p when t is 0 and state what does that quality present. So when we plug in t, we get to the 0 power. Remember, anything to the 0 power is 1, but that only goes to what's directly in front of it. So that tells us that p of 0 equals 28. So what does this quantity represent? So since t represents the number of years since 1990, when t is 0, that is 1990. So this means in 1990, the population was 28 million people. Well, then it asks in part B, what was the population in 2010? Well, if t equals 0 is 1990, 20 years later would be 2010. So our t would be 20. So we can plug that in. That gives us approximately 98.66. So this means in 2010, the population was approximately 98.66 million people. Now, notice the population grew. It was originally 28 million people, and then 20 years later, it became 98.66 million people. Well, we knew the population was going to grow because this base of b is larger than 1. Think of it again as a percent. 100% means you just get the exact same amount back. You multiply it by 1. Larger than 100%, you get the original back and then some. So basically, this b value is 100% of the original plus 6.5% of the original. 100% plus 6.5%. So it is, in fact, growing. Now, there are other types of exponential functions that carry a different base. And let's talk about that base first. It's called Euler's constant. I know it looks like Euler's, but it's pronounced Euler's. And it is represented by the number e. That e is defined to be the value where the quantity 1 plus 1 over n is taken to the nth power. And as n becomes really, really large, we're talking approaching infinity, okay? So in calculus, we get this idea a little bit more precise through the concepts of limit. So you guys will hit this later. But Basically, the number e is an irrational number like pi. We cannot write it in its exact form. Decimal form gives us approximately this value here. And e, that number is on your calculator, just like pi. So when we have an exponential function with continuous growth or decay, it is represented by the formula a of t equals a times e to the rt. So A is still the initial or starting amount, and A still has to be greater than 0. R is the continuous growth rate if it is positive, in other words, greater than 0, or the continuous decay rate if R is negative or less than 0, and that is per the unit of time. T is the time elapsed since the beginning, and it could be in minutes, seconds, hours, days, months, years. So again, if R is greater than 0, the exponential function increases, which means we have growth. And if R is negative or less than 0, then the exponential function decreases, which means we have decay. So in the second example, it says radon 222 decays at a continuous rate of 17.3% per day. The fact that it says continuous rate gives us a hint that we're going to use E. When we start with 150 milligrams of the radon, the amount is represented by the function R of t equals 150. So again, there's our initial amount, times e to the negative 0.173 times t. Again, it is negative because they told us it decays. So t is in days and r is in milligrams. It's asking how much radon will be left after 7 days. So they're asking us to find r of 7, which would be 150 times e to the negative 0.173 times 7. Now, if you're to put that in, let's say, a scientific calculator, you can put directly 150 e, and that e might give you a hat if you're doing e to an exponent. Just be sure that you have parentheses around that negative 0.173 times that 7, close the parentheses. In other words, be sure that you're telling your calculator that that entire product is in the exponent. Otherwise, if you're using scientific calculator, you can go ahead and multiply that, which will give us an exponent of a negative 1.211. And if we put all of that in our calculator, we get approximately 44.6849. So this tells us there will be approximately 44.68 milligrams of radon 222 after 7 days. Now, that e to the x, you can find that above your natural log function. So it looks like this, either capital L, capital N, or your calculator might use a lowercase l, lowercase n, usually on the left-hand side of the calculator. So you'd need to use your second function to get to that e to the x. Now let's take a look at graphing exponential functions by plotting points. When we focus on part A, we're looking at the function f of x equals 2 to the x. We can tell it's exponential because our variable is in the exponent position. So we can do an old-fashioned table, xy or x f of x. 0 is always a good number to plug in. Any number to the 0 power will always give us 1. So if you have a parent function like this, before you do any shifts or stretches, it will always contain the point 0, 1 for a basic exponential. Also, if we plug in the number 1 for x, you will always have your base to the first power, which gives you just your base. So in this case, we have the point 1, 2. Also, if we plugged in a negative 1, that gives us 2 to the negative 1. But remember, that doesn't give us a negative number. a negative exponent means reciprocal. So that means we have the reciprocal of the base. So when x is -1, our y value is a positive 1/2. Well, as we're drawing the graph here, I want you guys to pay attention to the left-hand side. Let's suppose we had x equals -10. Well, 2 to the power of -10 is the same thing as 1 over 2 to the positive 10. So it's still a positive number. It's really close to 0, but it doesn't equal 0, and it's not going to go below into the negatives. So when we draw this graph, I mean, we can go ahead and do 2. So 2 squared is going to give us 4. So we know the number goes, or the point goes right up there. But notice it's getting really close to hitting 0 on the left-hand side, but it doesn't actually touch it. So in this particular function where g of x equals 1/2 to the x, since our base is between 0 and 1, it means this is going to be a decreasing function. So again, if we plot some points with our table, we're going to plug in 0 again. So again, 1/2 to the power of 0 still equals 1. So notice we still get that same point of 0, 1. If we plug in 1 for our x, we get 1/2 to the power of 1, which is 1/2. So we get the base back. And if we plug in -1, we get 1/2 to the -1, which is the reciprocal, which would give us a positive 2. So we can keep going. So basically this guy here is the mirror image of the graph that we had before. But it never actually reaches 0 because our base is positive. So I want to talk about something called the horizontal asymptote. This is a line that the graph approaches as x goes either towards positive infinity or negative infinity. For example, in the first graph on the left, it's getting really close to this line here, which would be y equals 0, as x is approaching negative infinity. So as x is getting negatively large, it's getting really, really close to 0, like this number here. That's, it's approaching 0, but it's not actually equaling 0. Likewise, on the graph to the right, it is still getting close to this line here of y equals 0, but this time as x is approaching infinity. So those will actually be the horizontal asymptotes of a basic exponential parent function. So let's take a look. Horizontal asymptote would be y equals 0 before any transformations. The domain goes from negative infinity to infinity because we can use any x, but the range, notice it starts right above the y equals 0, and then it continues on up towards infinity. So our range would be 0 in parentheses because it never actually equals 0 towards positive infinity. There are no x-intercepts unless it's, again, shifted down, but there's always one y-intercept at 0, 1, as long as it's not shifted. So an exponential function will always be increasing over its entire domain as long as your base is greater than 1. It will be decreasing from negative infinity to infinity, those are parentheses, if your base is a fraction between 0 and 1. So again, you can think of it in terms of that base being a fraction or a percentage of your original amount. When we are graphing, the transformations work the same as before. Okay, the same as all other graphs. These transformation rules always work. So if we're looking at this generic form or general form of an exponential function where f of x equals a times b to the x minus c, so we're subtracting c from the x value, the input, and then plus d from the entire function. If the number in front of that b, let's take a look at its absolute value. So if the absolute value of a is greater than 1, then we're going to have a vertical stretch. Okay, it's going to be getting stretched up and down by a factor of that absolute value of a. If that absolute value of a is between 0 and 1, in other words, being multiplied by a fraction, then we have a vertical compression. It's going to kind of shrink down vertically by a factor of absolute value of a. And honestly, the only reason we're talking about the absolute value is that if we have a negative a, in other words, a is less than 0, then that's multiplying the entire function value by a negative. So whatever's up top is going to go down bottom, whatever's on the bottom is going to go up top. In other words, it's reflected over the x-axis. Now, if it's the x value that's being multiplied by a negative, in other words, a -1, then the graph is reflected over the y-axis. The horizontal shift, that's determined by that number, that c that's being added or subtracted from x. And remember, those inside changes, those x values works opposite that you think. So a horizontal shift by the absolute value of c is in the opposite direction of the sign of c. A vertical shift by d is in the same direction as the sign of d. So in example 3, we're going to use transformations to graph the function f of x equals 3 to the power of the quantity x plus 4, and then the entire function minus 1. And then we want to find the domain, the range, and if there is a new horizontal asymptote. Well, we first want to start with the parent function. So we'll say the parent function is g of x, which equals 3 to the x. So that's before we shift in any direction. So remember, with the parent function, we always have the point 0, 1. We have the point 1 and the base, so that's going to be 1, 3. Now, if we plugged in a 2 in there, that would also give us 3 squared, which is a 9. And the -1 would be a -1/3, and these guys are going to get really, really small. So it looks something like this. Also, with our parent function, I'm going to draw our horizontal asymptote here in kind of a lime green. I don't know if you can see it or not. I'll keep going. But our horizontal asymptote would be there at y equals 0. Now let's focus on the new function that's given that has some shifts with it. So we have 3 to the power of x plus 4 quantity, and all that's minus 1. Well, focusing on the x plus 4, remember that's a horizontal shift in the opposite direction of the sign that we see. So the plus 4 means we're actually moving left 4 units. And then the entire function, we're subtracting the 1. So that means we're going to move down 1 unit. So as we're graphing this, I'm going to take the point -1, 1/3, the first point there on the left. I'm going to move left 4 units, 1, 2, 3, 4, and down 1. So that's going to be roughly here. And then the y-intercept at 0, 1, we move it left 4 units and down 1. The point 1, 3, left 4 units and down 1. And the point 2, 9, left 4 units and down 1. But also remember, if we have a horizontal asymptote at y equals 0, that asymptote is also going to be moved down 1 unit. So we have to be careful when we're drawing the new function that we don't go below the new horizontal asymptote. So the domain of f of x doesn't change. It is still from -infinity to infinity. It's going to keep going. But our range has changed because the graph has moved down 1 unit. So instead of being above 0, it's now above a -1 to infinity. And where the graph starts, that's pretty much where our new asymptote is going to be. So our horizontal asymptote is now y equals -1. All right, if you have any questions, feel free to come see us, me or your teacher. Go to the Math Success Center, go find somebody to get some help. That's what we're here for. We get bored otherwise, so come on by. Thanks, guys. We'll talk to you later. Bye.